In this video we're going to look at ionic structure. The structure of a substance allows us to determine what kind of physical properties it will exhibit. By physical properties I mean melting points, whether they dissolve in water, whether they conduct electricity and things like that. So to start this off, we're going to go back and have a look at the compound that I looked at when introducing ionic bonding. That was lithium fluoride. We found in the ionic bonding video that I had a lithium ion, which was a positive ion because it had lost an electron, that was electrostatically attracted to a fluoride ion. To recap then, the ionic bond itself was the electrostatic attraction between the purple positive ion and the negative fluoride ion. Now to have a look at the structure of this compound. Well, all ionic compounds have a structure known as an ionic lattice. And what that means is that there is a three-dimensional structure whereby each positive ion gets surrounded by a negative ion, and each negative ion gets surrounded by a positive ion. So if I look at this by representing the positive ion as a purple circle and the negative ion as a green circle, I can see that this positive ion there will be surrounded to either side, above and below, by a green negative ion that's electrostatically attracted to it. But importantly, because this is in three dimensions, there is going to be a negative ion that's in front, and there's going to be a negative ion that is behind that positive ion. So just to look at that a little bit more clearly, we're going to look at the following diagram. Now you can see here in 3D that if my purple dot there represented a lithium ion, it's surrounded to either side, above and below, by a negative ion, the fluoride ion. But also behind it there is a negative ion, fluoride ion, and in front of it would also be a negative fluoride ion. So that positive ion is surrounded by 6 negative ions, and every negative ion is actually also surrounded by 6 positive ions. So this continues in a giant array, what's known as a lattice. There will be billions of ions attracted to each other in this lattice, okay? So this gives rise to certain properties which we're going to discuss now. So the first property to discuss is the melting point. We know that the melting point is the temperature at which the solid gets converted into the liquid. To convert the solid to the liquid, we need to break all of these interactions so the ions are free-flowing themselves. Now, if we consider that the attraction between a positive ion and a negative ion is quite strong, and each positive ion is surrounded by 6 negative ions, and each negative ion is surrounded by 6 positive ions, and there's billions of these interactions, what we can envisage is that to break all of those interactions is going to require a lot of energy, which means it's going to take quite a high temperature. So ionic compounds themselves have high melting points. So high melting points to break the very, very strong interactions between positive and negative ions. The next property we're going to discuss is the fact that they are crystalline. They're crystalline because there's a very regular array of positive and negative ions beside each other. So it's easy to form crystals of these substances due to the strong interactions between the particles and the ease with which they form this ionic lattice. So they are crystalline. Another property that we'll look at is the fact that ionic substances are brittle. Why are they brittle? If I applied a huge force to the ionic lattice, I would basically, let's say I pushed one row of these ions across. Well, if I pushed a row of ions across, then that negative ion would come into contact with that negative ion, and what we get is two negative forces which would repel each other, okay? And the positive would line up with the positive. These ions would repel each other and therefore break apart. So ionic compounds are also brittle. Another property is that most ionic compounds are soluble in water. They're soluble in water because they form favorable interactions with water molecules. So what we know in chemistry is that if something is likely to occur, then it's probably going to be energetically favorable. Now we're not going to go into the complete detail involving entropy and Gibbs free energy of this. What we're going to say is that if you can form more energetically favorable interactions, then something is more likely to happen. So we now need to see what interactions are going to be favorable. Well, for this to dissolve, first of all the interactions here have to break apart, which is not energetically favorable. But if you form more favorable interactions, then it's more likely to occur. To look at this, we're going to need to look at a water molecule. We know that water itself is a polar covalent molecule, which means it's got permanent partial charges and a permanent dipole within the molecule. What ends up happening is that the negative ion forms very favourable interactions with each of the partial positive hydrogens, and each positive ion forms very favourable interactions with partially negative oxygen of the water molecule. Now, as a salt dissolves, there's going to be billions of these very favourable interactions between positive ion and partially negative oxygen, and negative ion and partially positive hydrogen, and it is these interactions which allows something to become soluble. If something is insoluble, that basically means that the attraction between the positive and negative ion is so great that it doesn't want to be broken apart when introduced to a polar covalent compound like water. The last property we're going to talk about is the fact that ionic compounds conduct electricity when molten, i.e. in liquid form, or else when dissolved in water. So to explain this, I'm just going to draw out an image, which I've previously drawn out here. So I've got my lattice here and water molecule here. We know that when the lattice gets dissolved in the water, the ions are free to move. Well, electricity is the movement of charged particles, be they ions or electrons, so you just need the ions to move. And if the ions can't move, like when they're solid, it doesn't conduct electricity. Also, when you melt the solid, it becomes a liquid, so the ions are free to move, therefore it will conduct electricity. That's the last property we're going to talk about in terms of giant ionic structure. So just to recap, we have positive and negative ions really strongly attracted to each other in a giant ionic lattice, which gives rise to a number of properties.